Hello all, here is Aishwarya and I'm doing my BE in Electronics and Communication Engineering at Tyagaraja College of Engineering, Madurai. And in this video, I'm going to explain you all about a very interesting topic on amplifiers. Yes, it is all about the high frequency analysis of BJT amplifiers. And I hope you'll all be liking it. So what are we waiting for? Let's get started. We have all assumed that at low frequencies, the response of the transistor to changes of input voltage or current is very instantaneous, and hence we have neglected the effect of shunt capacitance in the transistor. But this is not in the case of high frequencies. And also, at low frequencies, we analyze the transistor using H parameters. But for high frequency, the H parameters model is not at all suitable because the values of H parameters are not constant at high frequencies, and therefore it becomes necessary to analyze the transistor at each and every point of frequencies, which is absolutely impracticable thing. At high frequencies, the H parameters totally become complex thing in nature. So due to these reasons only, hybrid model is used for high frequency analysis of the transistor. And this also gives a reasonable compromise between the accuracy and simplicity to do this analysis very easily. So what is basically a frequency response analysis of amplifiers is? We'll look upon it. The frequency response of an amplifier refers to the frequency range in which the amplifier will operate with negligible effects from capacitors and the device internal capacitance. And they call this range of frequency as the mid-range frequencies. And basically, the frequency response is one of the most important properties of amplifiers, and which directly depends upon the components and the architecture chosen for the design of amplifier. As we can see that in low frequency ranges, they are only considering the coupling and bypass capacitors, whereas the parasitic capacitance is laid open. And in high range of frequencies, the consideration is only for parasitic capacitance, whereas the coupling and bypass capacitors are being shorted. But in mid-range frequencies, the parasitic capacitance is laid open and coupling and bypass capacitors are being shorted, so that in mid-range frequency we get a gain that is called as AV mid or mid-band gain that does not changes at every point of frequencies and remains constant. Here also we can see clearly about the three frequency bands that categorize the frequency response of capacitively coupled amplifiers. It also shows the considerations of different capacitors that we use for frequency analysis. So with this info, let's move towards the high frequency response of a common emitter amplifier. Since the internal transistor capacitance that is created at the junction do come into play at high frequencies, the amplifier's gain is being reduced and it also introduces a phase shift between them. But at low frequencies, if we consider this formula, Xc is equal to 1 by 2 pi Fc, as the frequency decreases, the reactance of the capacitors increases. Since this capacitance value is also will be low, so as a result that the circuit is being considered open, so the effect of the internal capacitance will be neglected at low frequencies. We can also see that junction capacitance being created between base emitter junction, and we call it as CBE, and the junction capacitance created between base and collector, it is called as CBC. Now, here if we see a common emitter amplifier is being drawn and the internal capacitances have been mentioned. So according to the same formula, as frequency increases, the capacitive reactance decreases and it tends to zero. Ideally, at high frequencies, we consider the capacitive reactance due to the capacitors such as coupling capacitors and emitter capacitance, they will be zero, so that we don't consider them at high frequencies. And we have another capacitance called as a wiring capacitance, which are formed by contacts at the input and output side respectively. So we denote them as CWI and CWO respectively. And when the reactance of the base emitter junction capacitance becomes small enough, a significant amount of signal voltage is lost because of the voltage divider effect of the source resistance as well as the reactance of the CBE. And also, when the reactance of base collector junction capacitance becomes small enough, a significant amount of output signal voltage is fed back out of phase with the input. And this is basically a negative feedback and thus effectively reduces the voltage gain. Now let's see the explanation for high frequency model of a transistor. And this diagram represents the high frequency model where input resistance is represented by R pi, transconductance by Gm and output resistance by R naught. So we also know that transconductance is found out by taking the ratio of output current to input voltage, that is IC by VBE, and the small signal input resistance between the base and emitter, which will be called as input resistance, are denoted by R pi, which is equal to VBE by IB. And we also know that output resistance R naught will be equal to VCE by IC. Basically, in high frequency model, and a resistor and two capacitors are added in addition to the components in the low frequency model. So in figure, the point B dash, which is a point which is internal to the transistor and it is a part of the base region. And again, if we see the Rx resistor, that denotes the resistance between the silicon material between the external base terminal B and the internal base terminal B dash. Its value is usually less than 100 ohms and has significant effect in the high frequency response. And it does not have any role of in the low frequency analysis since the Rx value will be very less than R pi value. So next we can consider the base emitter capacitance, which is represented by C pi. This capacitance occurs due to the combined effect of the emitter junction diffusion capacitance CDE and emitter junction depletion capacitance CJE. So these are the most important capacitance that are formed due to the process of diffusion and depletion. And the base emitter capacitance value is between few picofarads to few tens of picofarads. Next is the collector base capacitance C nu, and it is the capacitance of collector base junction, and the value ranging from fraction of picofarads to few picofarads. In this image, we can see that it sums up the content about the internal capacitors. That is always the emitter base junction is forward biased. So both the diffusion and depletion capacitance are associated with forward biased junction. So the CDE and CJE forms the C pi. And the collector base junction is reverse biased and the depletion capacitance appear at this junction and that is represented by C nu. So now let us look into a theorem which helps us in understanding the high frequency analysis. That is called as Miller's theorem. Basically, Miller's theorem is used to simplify the analysis of inverting amplifiers at high frequencies where the internal transistor capacitances are more important. So this Miller's theorem play a very important role in the high frequency analysis. And AV is nothing but the voltage gain of amplifier at mid-range frequencies. And here in this diagram, C represented as CBC, collector base capacitance. And according to Miller's theorem, this internal capacitance CBC can be splitted into two capacitance, that is C in Miller and C out Miller. So let's see how they are being splitted into two capacitances. Miller's theorem states that the C effectively appears as a capacitance from input to ground and it can be expressed as a formula, that is C Miller equal to C into AV plus 1, and this Miller's theorem also states that C can be effectively appeared as capacitances from output to ground and it is represented as C out Miller equal to C into AV plus 1 divided by AV. And this indicates that if the voltage gain is 10 or greater, this C out Miller is approximately equal to CBC, that is C, because this AV plus 1 by AV will be equal to 1. So here in this image, we can see that the Miller's theorem is being used to analyze the high frequency response of a common emitter amplifier. So we have the source voltage, source resistance and R1 parallel combination of R2, and then input capacitance are basically two capacitance are included, that is CBE and C in Miller, and in the output side C out Miller is a capacitance included. And as usual we know that R out or RAC is represented as the parallel combination of RC and RL. And another important thing is that this common base and common collector amplifiers do not suffer from this Miller effect, since in these amplifiers one side is connected directly to the ground. So if we consider the common base circuit, the base terminal is being grounded so that the base collector capacitor does not affect the input and the input capacitance only equal to the base emitter capacitance, that is CBE. And at the same time, if we take the common collector circuit where the collector terminal is being grounded, the input capacitance equals the base collector capacitance only. So now, for the analyzation of RC circuit at high frequencies, the input side and output side are dealt separately, and at last we will be observing the total frequency response. So first, let us look into the input RC circuit. As shown in the figure, it has the voltage source, source resistance, and the R1 and R2 are in parallel combination. Then the input capacitances that are available, that is nothing but the CBE and C in Miller, and this HIE is obtained by replacing the transistor using the hybrid model. And further, the circuit is being simplified by using the Thevenin's theorem, that is, voltage source is replaced as V Thevenin and the total resistance is being calculated, that is equal to R Thevenin. It is the parallel combination of RS, R1, R2 and HIE. And again, it is connected to the total capacitance, that is the parallel combination of CBE and C in Miller. So if we see that as the frequency increases, the capacitive reactance becomes smaller, and this causes the signal voltage at the base to decrease so that the amplifier's voltage gain decreases. The basic reason for this is that the capacitance and resistance act as a voltage divider, and as the frequency increases, more voltage is being dropped across the resistance and less is across the capacitance. So, as we all know that at critical frequency, the gain is 3 dB less than its mid-range value, and which is just as with the low frequency response also. The high critical frequency Fc is the frequency at which the capacitive reactance will be equal to the total resistance, and this is given by the equation Xc will be equal to the total resistance, that is nothing but the parallel combination of Rs, R1, R2, HIE, and that is equal to 1 by 2 pi Fc into C total. With this equation, we can find the formula for Fc input, and that will be 1 by 2 pi into total resistance into total capacitance. And as the frequency goes above in the input RC circuit, it causes the gain to roll off at the rate of minus 20 dB per decay. So next, let's see about the phase shift for the input RC circuit at high frequency, and that is given by the formula theta is equal to tan inverse the total resistance divided by the total capacitive reactance. And if we see at critical frequency Fc, the phase shift is 45 degrees with the signal voltage at the base of the transistor. Since at the critical frequency, the total resistance will be equal to the total capacitive reactance, so tan inverse 1 will be absolutely 45 degrees. But as the frequency increases above Fc, the phase angle also increases above 45 degrees and it approaches towards 90 degrees. In this diagram, we can see that how the output circuit is being simplified and analyzed further to find the output critical frequency for this RC circuit. So here the RC is being combined with RL and made as a parallel combination. And if we see this beta AC into IB is again obtained from the replacement of transistor with its approximate hybrid model. And this circuit is further simplified into a simpler circuit using the Thevenin's theorem, where the output resistance is RC parallel with RL and the output capacitance is C out Miller. So using this, we can obtain the equation for critical frequency, that is 1 by 2 pi into R naught into C out Miller. And further, the phase shift and the high frequency output RC network is given by theta is equal to tan inverse the total output resistance divided by the reactance of C out Miller. So now let us consider about the total high frequency response of common emitter amplifier. And here, the two RC circuits created by the internal transistor capacitances influence the high frequency response of BJT amplifiers. And as the frequency increases and reaches the high end of its mid-range values, one of the RC will cause the amplifier's gain to begin dropping off. And more importantly, the frequency at which this occurs is called the dominant critical frequency. It is the lower of two critical high frequencies. And if we see at Fc input, the voltage gain begins to roll off at minus 20 dB per decade. At Fc output, the gain begins dropping off at minus 40 dB per decade because each RC circuit is providing us with a minus 20 dB per decade roll off. And this graph is the smoothened graph of this. where the curve is very smooth compared to this first graph. So at last we obtain the total frequency response of a common emitter amplifier, including the mid-band range, high frequencies and also the low frequencies. Whereas in mid-band range, every value of frequency, the gain value does not changes and it remains the same. Whereas in low frequency band, the gain falls off due to the effects of coupling capacitors and the emitter capacitors. And whereas in the high frequency band, the gain falls off due to the internal capacitive effects that are present in the BJT. But only in mid band, the capacitance can be neglected. Where here the y-axis represented the voltage gain in dB and x-axis represented the frequency in hertz, and we are considering a log scale. So now time to look upon into the advantages of this high frequency model. The main advantage of this high frequency model is that the model can be simplified to obtain the low frequency model of BJT, and this is done by eliminating capacitances from the high frequency model so that the BJT responds without any significant delay to the input signal. In practice, there will be some delay between the input signal and the output signal of BJT, which will be very small compared to the signal period. Signal period is nothing but 1 by frequency of input signal, and hence it can be neglected also. And the high frequency model of BJT is simplified at the low frequencies, and it also can be redrawn along with the small signal low frequency hybrid model of BJT. Yes guys, that's all from my side, and I really believe that this video would have been very informative and useful thing to you. I think I made it very interesting. So bye bye, here is Aishwarya signing off, and my heartfelt thanks to everyone for watching this video.